I welcome you here. Hello. So glad to see all of you here. My name is Oleg Selajev, and we're going to talk about performance and some performance tools and how developers and teams could think of performance for the better future. A couple of words about me. I work for Zeros Around, which is a company producing tools for Java developers. I'm located usually in Estonia, where it is currently pretty cold already. So I'm so happy to be here, even just for a day. I am a co-leader of Virtual Jug, which is an online-only Java user group. So if you are lazy enough to actually come to the annual Jug meetups, you can join us, and then you can join our sessions from the comfort of your home. How many of you have heard of Virtual Jug? Excellent. Less than half. The rest of you can check it out, just virtualjug.com. And so I also am one of the founders of GDG in Tartu, which is a small town in Estonia. And at Zeros Around, I'm a developer advocate. My main responsibility is to care about community of Java developers. And I maintain our blog called Rebel Labs, where we publish technical, opinionated content. So if you check it out, I will be personally very happy. So before I was a proper developer. So enough about me. Let's talk about performance. Performance is pretty hard, and it's also a very interesting topic. And as head of Rebel Labs, what we do, once a year, we run a survey of Java developers. And we ask everyone we can reach to over social networks and everything, and we just try to gather some insight about how the community operates, what tools they use, and so on. And we also ask a couple of questions about software architecture, development practices, and so on. And we also asked questions about performance. This year report, we got some results back, and I wanted to share those with you. So first, how do people treat performance in general? And surprisingly, very many people either don't care about performance, well, they say they care about performance and performance is important, but they don't really do anything much to actually ensure that the performance of their code is reasonable or stays reasonable over a long period of time. You can see that almost 40% either don't care at all or just do that fully reactively. So they throw the code over to the operations deploy it, or they run it themselves, and they wait for users to complain that stuff is slow. How many of you use this approach? Not judging, because it is complicated, but this is a very typical thing. And then when we ask them a follow-up question, why do they approach performance work this way? We got a different result, which is very confusing. So almost half of the respondents say that, yeah, performance is really important. It influences the baseline of our product. And if you imagine if you're working in a bank or e-commerce, if your users cannot actually check out the cart, well, you're losing money, especially when there are spikes in traffic. But almost 20% of developers said that they don't know how to properly approach performance work because it's hard. It's not really, there is no entry point into that. And you have to do that properly, right? It doesn't make sense to just do nonsensical things. So you have to understand how to write benchmarks, you have to understand how to use tools, you have to understand how to build up the process, and it's very non-trivial. And the proper performance experts, those guys and those people are very expensive because of their time. Indeed, they put a lot of time and money investing into the expertise, and now they charge for that. So in this session, we're going to look at a thing that we call the performance pipeline, a methodology to take care of performance more proactively, not to wait for the user's complaints, and just think about what you can do in your projects regarding the performance to at least make a couple of steps towards a better process. So when we talk about performance, one of the biggest misconceptions is that you have to do that properly. You have to write proper benchmarks, you have to use like sophisticated tools, you have to know what you're doing, otherwise it's completely irrelevant. And at some point, and in some situations, that is correct. If you see the performance people somewhere in the social media, on Twitter, they will be handling those low-level operations, trying to make the code much faster, and indeed that would be very hard to replicate on any typical project. So say 1, 2. Oh, excellent. Sorry. It's actually not the AV people's fault. They heard the sound before and they asked if I wanted a different headset, but then the sound disappeared. And then I was like, yeah, fine, we're going to handle that. Well, the reality kicks in. So when you do performance work, it doesn't matter that you cannot build the full environment and the full process as you would see, say, OpenJDK developers do, right? They work on a very low level, they do hardcore stuff, and their requirements are not typical requirements for applications. How many of you work on web applications? Yeah, and this is what I thought, almost everyone. So, and Java can be used in different contexts, but mostly what people use it for are the backend development or like a full stack development, but we talk about web applications. And that applies a number of constraints of what we need to do regarding quality, performance, and so forth. If you think about a typical web application, it looks like this. There is some sort of a front end, there is some layer of a backend services. It could be like one monolith or like a bunch of microservices or distributed monoliths or whatever you fancy. And then there is a data store somewhere from which you take the data, then you somehow transform that data and show it to the user. So this is what typically web applications do. And that puts on a set of constraints. And we're going to talk, in this session, we're going to talk about the performance monitoring and performance work for typical web applications. So what does that mean? That means that our users will be humans. We are not going to be talking about the financial services which consume millions of messages per second, and they have to react in a very timely manner. But we're going to talk about normal web applications where users look at the screen, make an action, click a button, then the data comes back and forth, they look at the screen again, they analyze what you show them, they think about this a second, they do something else, right? They can do that pretty fast if they're experienced, but still there will be a delay. It's not going to be a single user bombing our application with requests like millions of times a second. The second constraint is that our data will come from elsewhere. We are not going to be talking about those systems which, as I said, messages come in, you have to react to that data and put out the answer immediately. But with a typical web applications, you will have a data store or multiple data stores, and you will combine the information and show that to users. And what we're going to talk about is mostly those applications have two types of performance issues. It could be scaling, and where the throughput is just not enough. And the easiest and most typical solution is just to throw money on the problem and buy a more powerful hardware or just scale the number of machines. And the second, we are not going to talk a lot about those, but the second type of the issues is that there are some operations for some users that are slow. So typically, I would expect that we would not write the code that is terribly slow in the first place. It's not our goal, but in some situations, for some users, some certain operations will be unbearably slow, right? And we would like to actually actively avoid those in the first place. Does that sound like a typical use case for people here? Excellent. So if we talk about web applications and we run those reports, as I mentioned previously, for a couple of years, one of those was about the performance work and performance tools people use. And we asked what typical issues, performance issues, and what are the root causes for those issues that you find in your application. We got the results back. And the results were that almost half of the issues are not about the code that you write, but there are some certain events in the system that take long time. So that would be the handling of the database. That would be the handling of the network resources. Of course, plenty of issues would be just because you write code that has an algorithmic complexity of something trivial but maybe not optimal. And there are some issues with memory. But mostly, the issues come from those individual events in the system. So you are either retrieving too much data, or you're going to database too many times, and come back with the answer. when we asked where do people actually monitor the performance and where do they do the performance work, we got the results approximately like this. So almost a third does some performance work in development. And this is very natural because that's where the developers are. And as we know, well, developers are to blame for everything, except when the operations are in play. Then we don't like those guys. And a lot of people, especially the operations teams, because they care and they live and breathe performance every day, they do monitor the application state and how it behaves, and they do work on the right hand. But one insight about all software development and about performance work in particular is that when we asked who fixes the performance issues, the overwhelming response is that it all comes back to development, right? Some issues you can solve in production, for example, scaling, but most of those, especially the issues that come from the code, they cannot be solved over there. They need to come all the way back to the developer. A developer has to look at the code, figure out what's happening in the code, figure out why this particular thing could be slow, and then they fix that. And then it goes back over the fence. So why is this terrible? It's not terrible. That's how it is. Why is it inefficient? Because it has to go all the way back to development, which takes a lot of time. And time will equal money. Why do we continue doing business this way? Very simple. Because when you talk about software, there are a couple of requirements that the software has to satisfy. So first is functionality. Functionality is necessary to provide any value to business at all. So we care about that, right? Second comes quality. And we mostly figure out how to provide quality software to the client. We run the unit tests as early as possible. We run the integration tests. We have the QA teams that will figure out that actually what we did comply with what the client wanted. Then on the third place, it's performance. If we're lucky and we have time in the sprint cycle, we will do something with performance. On the last place, there is security, and those people are in a very poor place. So almost no teams, very few teams actually, have resources and have discipline in the process to go lower than the functionality and the quality. So what I want you to take out from this session is that performance is equally important as quality. If your application is slow, it's unusable. And what I want you to think is that since you know that you will be the ones who are fixing the problems, you as well might be actively aware of whatever you do might influence the performance, and you think about performance proactively rather than waiting for the complaints, because they will come. And you know, yeah, the security, sorry. So you know, see, no one remembers about security. Hopefully that's not true. But what we know is, and from the quality perspective, we know, and we run the survey, and not us, by us, I mean the community. We know that when the issues are discovered in production, that's way more expensive to fix rather than when they are discovered early. That's why almost any sensible team will run test suites as often as possible. They will run the continuous integration environments with tests to try to discover bugs early so they can fix them very cheaply. And the difference is like hundreds of 2 orders of magnitude. So let's agree that we should do performance work more early. Another aspect of performance work when we think about this is there are different kinds of performance work. So Alexei Shipylev, he was for a long time the performance engineer at Oracle, working on OpenJDK. And now he's at Red Hat, one of the lead developers, I think, of the Shenandoah garbage collector. He's doing a lot of performance work. And he tweeted that once, the Shipylev's curve of performance. So if you think about that, when you start your application and you write a code for the first time, this is probably the simplest thing that works, right? If you are using test-driven development, you write your tests first, then you write the code to satisfy those. But it's not the most sophisticated code. It's just something that works. So, and we are there in the A point. Probably this code will be more complex and less elegant than it should be or could be, and probably the performance of this code will not be optimal. On top of that, we can move into a different place, to the B, the beauty peak, where we simplify the code, we refactor it. Probably the compiler and the infrastructure and the JVM will be, the simpler the code is, the easier it is to optimize for the tools, right? So it probably will be more performant, you will do less work in the code, and it will be easier to read. So we would like to be here. On top of that, you can do all kinds of tricks, and then you can micro-optimize, and you can reach the unmaintainable but really, really fast code, which is typically not necessary, especially unless you have like super strict performance requirements, which is a good question as well. How many of you have performance requirements for your applications that you're working on? That's amazing. You're in a good shape. So what we want to talk about now is how to get from point A to point B, where our application is sufficiently readable, where we don't introduce any hacks that sacrifice the quality of the code and maintainability of our code for performance. So we are not going to talk about using unsafe to quickly swap an int in memory, because that's something that almost no people should do. But we're going to talk about what tools and what approaches are there to take your code that kind of is functionally correct and is working, and then make it faster and make it avoid unreasonable performance regressions. So let me introduce the performance pipeline, which is a mental concept and model that we came up with, which is similar to the software development pipeline, where you have different stages of software development, and we're going to look at what work you can do and which tools you probably should be using at all those stages. And we start with the first one, which is design and requirement analysis. It's not the time to test your application, so it's not the time to collect any performance metrics, but it doesn't mean that you shouldn't be thinking about performance of your code while you are designing or collecting the requirements. What you need to do at this stage, you need to figure out what are the performance requirements for your application. You need to write that down. You need to set up measurable goals of how your application behaves. Most preferably, it shouldn't be, oh, let's write the code that is fast. It should be expressed using some metric that is collectible. For example, it has to have a throughput of that many requests per second. It has to handle that many concurrent users. And, for example, the latency of a certain request should not exceed, on average, or like at 95th percentile, it shouldn't exceed a certain number of milliseconds. So even at the requirements phase, you have to think proactively about performance. Then it comes the design stage, which is also very similar to the requirements gathering, because there is no actual code and there are no artifacts, so you cannot actually do performance work at this stage. But you have to think about this, and you have to understand that the choices that you make at the design phase, starting from application architecture, what libraries and tools you are going to use to implement your software, that will influence your performance metrics. If you are running everything in a single JVM, that's completely fine. And then at some point of time, you will go into a cluster, and their performance metric will change even before, because you just have multiple things, so you have an additional network hop or something, and that all will influence. If you're going with a fleet of microservices, you will have maybe a better time maintaining this application code, but there will be multiple hops, and that will influence the latency of the requests as well. So you think about that, and you plan ahead for the performance work. And then comes the development. Yoo-hoo, because this is where most of us work, and this is where most of the work will continue. So when we talk about development, the important question of all performance work is that what are the metrics that we are trying to improve? What are we going, so when they are failing, why are they failing? How do we collect the metrics? Why the application is slow, where in the code I have to change things, and then when you change the things in the code, you have to verify that that change was successful, right? So those are literally basically two main questions of performance. Where do I need to change the code? And when you change the code somehow, because there is no recipe how to make your application faster magically. That would be amazing, but sadly that's not the case. So where and verifying the results. When we talk about performance tools in development, probably the most known category of a tool will be the profiler, right? And they come in different forms, shapes, and pricings, and licensing agreements, but there are many of them. What a profiler does, it shows you the spread of where did the time go. There are different approaches of how to profile the application, but mostly you attach it to your running process, you apply some load, and then it gathers metrics and shows you where did the time go. So an example, and the simplest thing that you can do in development, even when your manager doesn't give you time to do proper performance work, you can attach a profiler to your application, and you can run some load on that, even if it's just like you clicking around, and you can look at the results. So what a profiler gives you, this is the JVisual VM, which is built into OpenJDK distribution package. So all of you have that. You just run JVisual VM from the command line. It will run. It will show you a screen like that. You will pick up which process you want to attach to, and it will start gathering some metrics. So most important ones will be what your CPU is doing. So where does your hardware spend time processing the data, some memory requests, and so on. So what you can do, you can enable the CPU profile. That is one of the tabs on the top. And then you run the load, and as a result, you get a table like this. You will have a number of methods, a list of methods that will show you which code was executing the most during the time where you're profiling your application. So two things about this view. First, it's very important that you understand how to work with this. For the untrained eye, this table doesn't show that much information. And we can see that, yeah, some methods take way more time than other methods. But you have to understand that you have to have a certain level of expertise to interpret those results. So gathering metrics in development and using a profile to gather metrics is quite easy. Does it help a normal average developer on your team to interpret those metrics? Not so much. Because if we look at the example, if this is something I run a Spring application here, and we looked at the results. So the most time-taking method is a task queue poll, which means that most of the time while we're running the code, something is just polling from some task queue. You can see that it's a Tomcat, its method and the class comes from Tomcat. So the reason, if you look at this with an untrained eye, it means Tomcat is slow, right? Well, the profiler told me that Tomcat is slow. What's the obvious conclusion? You need to buy a larger application server. Or maybe change your JVM. Unfortunately, that is not true. And if you think about the why, because the profiler gathers the information about the whole JVM, about what's happening on the whole thing, so it has very hard time to help you to understand why certain operations are slow. So in general, the profilers will be absolutely incredible when your application is slow all the time. So when you face scaling issues, if you don't have enough resources, you can, or if you run a very isolated method, you want to figure out how to make it faster or what takes time in that method, you run a profiler, you get a profiler, and you understand when everything is generally slow and equally slow, a profiler will show you, oh, out of that slowness, a certain part takes more time, and you find out the bottleneck. If you talk about the normal web application, you have to have a very certain mindset to decipher this table that I showed you before. So the profiler shows you what is the hottest code and where is the bottleneck, what you need to optimize. It shows you what is the bottleneck, but profiling individual operations with a normal profiler is not so easy. And you have to understand that. So a profiler is something that should probably come not as a first tool when you're trying to do performance work on the typical web application. You need a better visualization tool. You need to better understanding what is currently slow. If we talk about profilers, I just wanted to take a moment to point your attention to the thing. So very recently, there is a trend that tries to popularize flame graphs, which is the visualization of the profile just like the table that you saw before, but it comes in a different shape. So you just collect the stack traces, and you can do that either manually or with the tools that Flame Graphs provide you, and they paint you pretty pictures about that. So the thing is, the longer the span is in the thing, the more stack traces that you gathered have that element in the stack trace. So you can see that it all starts with the bottom level, and then those individual flames are the methods that you operate on. So somewhere in between there will be the Tomcat, and the actual letters there don't matter. It's a picture from the internet. But somewhere there will be Tomcat, somewhere in there will be your code, and you can visually see how much of the resources your code is taking versus how much the garbage collection is taking, and so on. So you can use tools to help you visualize and narrow down the bottleneck. So the second thing is, when you talk about performance, you talk about benchmarks, right? You need to measure things. And even with a profiler, you can find the spot where you need to optimize the code, the bottleneck. You need to verify that your application code became faster after the results of your changes. So you talk about benchmarks. And benchmarks time code execution. And you can see the numbers. The most important thing about the benchmarks is that you need a benchmark. You need to establish a baseline. Whenever you talk about performance, it very rarely makes sense to talk about performance in the absolute way. So it's rather hard to say how much actual time a certain operation takes. What mostly people are interested in is that we have a certain baseline, we have certain software requirements for the performance, and we would like not to go beyond those. Or when we talk about the changes to the code, we would like to have the changes that make things faster. But not like 7 milliseconds faster, but we need a trend. Why is this important? Because when your application becomes slow, typically they don't become abruptly super slow because someone committed something stupid in the code, right? Typically, you add more functionality, you add more code processing, data processing things, and your application becomes gradually slower and slower and slower, and it's like that frog that is boiled on the mild temperature water. Like when the frog is boiled, when the frog realizes that it's boiled, it's too late. So your application dies from the performance reasons the same way. It becomes gradually slower until the point where the users complain, but it's very hard to actually understand why is it slow now, because those changes you introduce over a span of time. So you need a baseline to establish performance requirements. And when you change the code, you need to confirm your improvements, and also as any benchmark, as any tool or any data, the results of the benchmark will require some interpretation and will require some relationships to the actual performance goals that you put in front of your application. So a typical benchmarks look like this. So what you do, you take 2 timestamps, and then you execute some code in between, and at the end you print out how much time those operations took. Who thinks it's a good benchmark? 2 people. Who thinks it's a decent benchmark that is reasonable to use in certain situations? That's a very vague political answer, so all of you agree. So what you probably want to do is, we'll come back to that slide. What you're probably more accustomed to see when people talk about the benchmark is that you have to use certain tools. For example, a good tool to use for benchmarks is a Java micro benchmark harness, which OpenJDK developers use to profile and benchmark the implementation of the JVM. And what it will do, it will take care of very many things that normal developers will implement wrong when building benchmarks. It will take care of the just-in-time compilation optimizations. It will take care to run your code under load, so you have the concurrency issues and everything figured out. And it's pretty simple to run benchmarks like that as well. But what you need to remember is it still will require some interpretation of the results. How many of you use JMH? Cool, 3 people. So for everyone else, JMH, Java Micro Benchmark Harness, if you are going to write benchmarks, consider using that. It's way harder to shoot yourself in the foot writing benchmark using that rather than just using 2 timestamps. For those who use that, I recently discovered that there is a thing called JMH Results Visualizer, where you can drop the JSON results, and it will actually show you pictures, so interpreting the results will be much easier. So you can Google that, and this is fantastic. Coming back to this slide, well, this slide, right, where you said that this is not a very good benchmark. Actually, I don't disagree that it's not the best benchmark ever, but this is something that's very easy to roll out. And if you talk about web applications, this is pretty reasonable benchmarks as they go. What do? You use this approach for macro benchmarks. When you don't try to figure out how fast a certain isolated piece of code works, but when you look at the larger picture, there is nothing wrong with this approach. And as you remember, before I advocated for using performance tools and thinking about performance early. So as a first step, you should introduce something like that into your build or into your continuous integration environment. The easiest way to do that, you have the tests, right? You have the integration tests, and some teams have the acceptance tests, where you actually use your applications through UI. Isolate a subset of those that covers most essential workflows for the users, and then create a job in your continuous integration server that will just take the timestamps and see how long those operations run, and then monitor how much time that job takes. And if that job abruptly takes more time that it took the previous run, you can be pretty sure that something went wrong. And that problem will discover itself in production later. So using benchmarks that are very simple, for micro benchmarks, it's no-go. For macro benchmarks, the large benchmarks, this is pretty reasonable. So do that. There is no reason not to do that. It will take you literally half a day of work, probably, if you're slow. So this is what you do in development. You run your benchmarks, and you use, say, a profiler to figure out the code. When we talk about testing, the test environment, right? Test. This is the stage that actually it's an umbrella stage for all main areas of testing that we do. The continuous integration environment, when we run the tests, the traditional performance and load test environments when we run performance tests, if we do run them, and the, say, almost up to the staging environment where we give the application to the actual or semi-actual users, like say a QA team, where they will use the application like normal human beings, and then will report the results back. So, and here I would like to introduce a tool by Zero Turnaround, which is an APM for development and test. What it does is, typically APMs are used in production, and in according with this performance pipeline thing, we wanted to bring those closer to development. And we made a bunch of technical choices how to build it and what information to display to show you, to make it more usable for development. This is where I would try very quickly to show you how it works. So let me just mirror my display. You can see that, right? Oh, excellent. So what is ExtraHub? ExtraHub is the software as a service platform. It's a cloud dashboard that collects performance metrics about your application as you develop them. So don't go back, the internet is terrible. So what it does, you have the deployments of your application somewhere. It doesn't have to be a staging environment or the load test environment. You run your application in continuous integration with integration tests, or you give it to QA, you deploy it somewhere. So it doesn't make sense not to collect some performance metrics about how your application performs in those environments. Yes, this is not exactly the same, and it's not 100% true metric about how it will perform in production, but there are very many things that you can catch up early. And if you remember the Shipyle's curve, going from the trivial but not very performant solution to the elegant and more reasonably performant solution could be pretty easy. So what ExtraHub, the main goal of that is to establish a baseline for the performance of your application, and then to allow you to monitor for regressions while you develop your application. So typically, you would how to instrument your code. It's a Java agent, so when you run your continuous integration tests, you just slap a Java agent parameter, provide a jar file, and it will collect some metrics and will send it back to the dashboard, and it will show you the results like this. So the main view here, and the main thing that it does for you, it can compare multiple versions of your application with each other. And you select the versions, and typically that would be the next commit with the previous commit, or the next commit with the version that is currently in production. And what it gives you a view that shows which endpoints in your web applications became slower. And it shows those extremely beautiful graphs that show how much slower the requests became at this endpoint in general. So if you see a lot of red, they became slower. You can see the actual numbers of the requests, how many of those requests were affected, and some other data. I clicked on that, didn't I? But the thing is, good thing the internet is slow. The thing is, what it does, it sorts all the request processing times into one row based on the latency. And then it compares percentiles of how slow became the fastest request for this endpoint with how slow the slow request became. So you can see that in this graph, the fast request didn't become slower. It's the medium slow request became slower. The good thing about ExtraHub, and I will not click on that because I think it won't load. Oh, it might load. What's the best thing about that is when you know it's slower, you would like to know why is it slower. So this is taking longer than expected, so I will show you the next page immediately. So for those requests, ExtraHub shows you a tree of execution. What happened while your server was processing that request, and it will show you a diff between the fast requests or the requests from the previous version and the next one. So you can see that there is new code that was added in this, and it took a lot of time. It took a lot of time because we do a remote request to a different service, and obviously that will take a lot of time, and you can see exactly what was added in the code during this request. And this is the way how you can figure out where the request got slower. So you violated the, what did you violate? You violated some baseline, and now as a developer, you see where you can fix things. There is a thing called extrahub local, and oh crap, cancel. Just run it. See, this is very bad when there is no network. There is a corresponding tool for the development environment. It's also a jar file. You instrument your application with that. You start your application normally, and then what it will give you a widget inside your application views, and it will show you the same trace of what happens during the request on your local machine. And then you can compare, and then you can see the same view in your application. Hopefully this Spring Pet Clinic application will start pretty soon. Let's see if it did. Where's my pet clinic? Here, boom. Go away. So, no, it didn't. Yeah, it did start. What it does, it shows you a widget like that. So when you go into this endpoint, which became slower, what it can show you, it shows you what has happened during that request serving, highlighting the events which we know are slow, like database access, network access, and so forth. And then after that, you can just see that on your development environment, you fix that, you verify locally that you actually fixed the problem or made some steps improving that problem, and then you commit the code again. So with those two, you can turn your continuous integration environment or load test environment into a performance test with very limited effort and time investment on the development part. Obviously, in development, one thing which is really bad for performance work in development is that you are running a single concurrent user, clicking on very few components of your application, and that is a very isolated testing. It can catch a lot of problems, for example, the database access, especially in the components that you just created, but it's not statistically that significant in the whole application in the grand scheme of things. So what you need to do, you need to write load tests or performance tests. So typically, there are a couple of libraries that are used for performance tests creation. It would be either JMeter or Gatling. And a more sensible approach currently is to run Gatling. And Gatling is a load test tool, which is you just download the jar file, you start the recorder. Let me just show it to you. Recorder. What it does for you, it starts a Java application. You configure a proxy to record all the requests that you do in your application. So what it looks like that. You configure the data that you want to gather. Then you go and use your application normally, and it will record everything that you do with your application. JMeter has the similar UI as well, but currently about Gatling. And it will record, and it create a simulation file that you actually can edit normally. It's a Scala DSL, but it's a pretty readable one, as Scala code goes. And you create a simulation. I think I have one of the simulations open here. So what I did, I instrumented my pet clinic with that proxy to create a simulation. Then I went into my application, clicked around like a mad user to actually write down what actions your user are expected to do. And it created a Scala file for me, where you can see that we create a scenario JFOL, and then we execute HTTP request to the home, then we pause for a second, then we go to the owner's find, and then we execute a bunch of requests with tons of headers. We see that our application tracked some data, and so on. At the end of this thing, we execute the setup. So the good thing about Gatling is that you can very easily have very many concurrent users with just one single line of code that is pretty readable. So in this scenario, we will have 100 concurrent users that will ramp up to through 12 seconds, and then this is a simulation file. After that, you just run your code normally, you deploy your application. It could be staging environment, a load test environment, or your development environment, just to generate the load. And you run it with the Gatling command. So Gatling. Maybe this will work, maybe this won't work. It didn't work. So you select the simulation, and then it starts working. The good thing about Gatling is that it's very efficient itself. So if you run this in development environment, the actual overhead of running Gatling is much lower than you would have with running JMeter. So those requests are created asynchronously. So the actual resource of your machine will be for serving those requests back through your application. So you can easily run that on your development environment to apply the load to your application, or you can easily configure that to run as a performance test. If you combine that with any performance monitoring tool in your performance test environment, you will get very valuable data. It could be an APM that you use in somewhere in load test environment. It could be ExtraHub if you want to use that. It could be just a profiler that you attach to your application. When you apply load in large numbers to your application, that downside of the profilers that they require your application to be generally slow will not be such a downside, because your application will be generally slow if you apply more users that it can handle. So you will see very valuable information. So it runs all that stuff, and then something timed out, shows you, come on, stop it. And it shows you very pretty, this is the simulation setup, it shows you very pretty pictures like this, showing about how your application behaved. It will show you the percentiles and how fast the requests were processed, and you can use that and turn that into a continuous integration environment job that will take those numbers and fail if your requests are slower than a certain baseline. Why you need to do that? Because you need an efficient process to care about performance through the whole pipeline of software development. There are plenty of graphs, but there is no time. So let's go back to the presentation very quickly. So I would recommend using Gatling in test. And this is the Gatling demo, which is still running very warm machine. Now staging, the next stage of the software development pipeline. What it does for you, it tries to replicate the production environment as close as possible. So you probably will use the same hardware or the same cloud. You'll probably have the normal users going around there. The only thing is that the data will not be real in staging. So you might use anything from the production environment if your local laws allow that. Typically, probably it would not be. But the thing is, if you don't use the staging environment to verify and monitor performance, you will do that in production. So in production, what you will have to use is probably an APM. There are also very many of those. What the APM is, the application profile monitoring thing, and it will instrument your app. It will act as a profiler, most probably. It will also act as this tracing thing that will show you which individual operations were slow. A normal APM will allow you to group requests from a single user into a single view, so you can isolate that slow user and isolate which operations were slow for them. So it will help with debugging a lot. It will also show you which requests are slow, and for slow requests, it can show you not the full spread, but it will show you the methods that take the longest time. And this is new Relic, but you can use anything that you would like. Dynatrace, AppDynamics, New Relic, and so on. The thing is, that is very largely, the production is the operations line, right? They handle everything in there. And they probably do that already. But that information is not, it's useful for a developer, but it's not always that useful, because to do performance work properly, you need to not only find where the things are slow, but also verify if your changes actually did any good or not. So working with an APM in production will not help you with that second thing that often. If you deploy twice a week, not twice a week, once in 2 weeks, well, you will have to wait a couple of cycles to verify that the things that you changed are faster. But it doesn't mean that you shouldn't use those. Also, what you can do, I have just 1 minute. What you can do, you can use the Java Mission Control, which is a profiler. What's great, it comes with a flight recorder feature, which is, you can instrument your application to run with that, and it will collect some metrics about your application very efficiently using the low-level probes, and then you can analyze that information offline, so you don't have to apply that overhead as a typical profiler will do on your code. So the best thing about that is you can not just monitor all the time and write that data to disk, making things slower, but you can use the metrics and hold them in memory. And when things become slow, configure it so now, OK, we're slow. Let's dump that information into the file. And then you analyze that chunk of information that actually could show you why things became slower. So, and it will show you CPU, memory, allocation, and all that things. And that comes from the Java Mission Control Center. And it shows you the views like a normal profiler. So all that thing, what we wanted to achieve in this session, we wanted to take this picture and make that blue thing as long as possible. So if you think you could spare some time during your development cycle to think about performance and to start using proper tools for performance work, that would be a great step forward. If you do that already, that's great. You can always improve. But if you don't, remember, you are pushing code to the production, it becomes slow, and then you are one to blame. Thank you.